Professor, we will start really soon. I will give a brief introduction of
Yeah,
you as our distinguished speaker, and then you can start.
yeah, thank you. Go ahead.
Okay. Hello, everyone. Welcome to our DDLC seminar today. Today we have distinguished invited speaker, Dr. Evangelos Theodorou. Hopefully it's correct.
Yep.
Dr. Evangelos Theodorou is an associate professor with the Daniel Guggenheim School of Aerospace Engineering at Georgia Tech. He is also the director of Autonomous Control and Decision System Lab and also an Amazon scholar. Dr. Theodorou is affiliated with with Institute of Robotics and Intelligent Machines and also the Center for Machine Learning Research at Georgia Tech. He holds a bachelor's degree in electrical engineering from TUT in Greece in 2001 and three master degrees in production engineering from TUT in 2003, computer science and engineering from University of Minnesota in 2007, and EE degree from USA in 2010. In 2011, he graduated with his PhD in computer science from USC, and from 2011 to 13, he was a postdoc research fellow with the Department of Science, Computer Science and Engineering, University of Washington. Dr. Theodorou has received the Consun Fu Best Paper Award of IEEE Transactions on Robotics in 2012 and also received several Best Paper Awards and nominations in machine learning and robotics conferences. His research spans the areas of stochastic optimal control theory, machine learning, dynamic and distributed optimization with applications to robotics, autonomy, and large-scale systems. Uh, let's welcome our speaker to start today's talk.
Thank you very much, Shanting. I hope that I pronounce your name well. I'm really excited to give this presentation. Thank you very much for giving me the opportunity to present my work today. I want to say that I'm presenting my work that I'm doing as a professor at Georgia Tech and the work that I have been doing in my lab over the last few years. So that's the work that I'm going to be presenting. And so I'd like to start by saying that optimization is pretty much everywhere. We see optimization in many different applications and use cases, and I just want to name a few of those applications from transportation to swarm systems. More recently, we see a lot of interest in data center management. There are a lot of interesting large-scale optimization problems in this space as well. We have also there's a lot of interest right now for satellites. There is the number of satellites in space increases. That's a big market. So there are many interesting optimization problems as well in this application, and of course air traffic management. And then there's the space of autonomous systems, so autonomous vehicles from systems that are that are operating in urban environments to autonomous vehicles that are operating in off-road environments to flying vehicles and hopefully in the future to air taxis. So these problems have some common characteristics, and here I just want to point out some of these characteristics because these things will come up later in my presentation. Many of these use cases are large scale, typically have to do optimization for many decision variables. There is always uncertainty that you have to take into account, and uncertainty and scale go together in the sense that whenever you try to take into consideration uncertainty, that has always a multiplicative effect in the scale of the decision-making problem. In many cases, you really have to take into consideration constraints and guardrails. Many of these systems have high socioeconomic impact. And also, I want to point out that not in all of these cases we have data from human experts. So actually, I would say in the majority of these cases, there's no an expert from which we could learn control policies. And so what I really want to talk about today comes from my own experience working with different types of optimization, starting from the days of my PhD when I was really trying to understand how can we use stochastic optimal control for problems in robotics, to later years as an assistant professor where I start working more on model predictive control for like smaller vehicles, to actually then more recent years working more with more challenging systems of bigger size and taking a lot of these ideas to the real world. And here I just want to contrast the space of autonomous driving with a lot of recent developments in vehicles that actually operate in urban environments where the key technology is to learn from a human expert, all the way to taking these vehicles to an off-road environment where really learning from an expert is a little bit more challenging because there are many environments. And so the problem is a little bit different in this application. And so there's an ongoing discussion. I have heard many experts, AI experts, talking about all of these different use cases, right? Like we start from reinforcement learning to then reinforcement learning together with imitation learning, and then we have a lot of people also who have been working on model predictive control, including myself. And then more recently, there is this interesting work that aims to combine both. And I really have to say that I'm really not a proponent of reinforcement learning. Having worked in this space, it's really very hard to get RL to work on anything real from scratch. And so the message really that I want to convey here is that based on my experiences, rolling oranges on optimization and MPC is really the only viable option when there is no expert or human operator to learn from. I just want to also point out that it is one thing to say that MPC is the future of AI, because I have heard many people talking about that, but also it's another thing to actually demonstrate it to the real world. I don't think that just only staying in simulation is the way to go. I think that we have learned so much by taking systems out to the real world. It's only when you take things out to the real world you can ask the question of what is the right architecture. Then RL never really works from scratch. Needs a lot of data. You really always have to have a very good initial policy. People have combined it with imitation learning, and this is a viable option. But again, in this case, you have to have a lots of data. And then I think as scientists, we should always seek for interpretability. I think I'm really a proponent of optimization because it is definitely more and more interpretable path. And then another point that I want to make here is that this issue of human expert does not only appear, the lack of it does not only appear in use cases in autonomy, but it appears in a lot of other applications where we start to work with very large scale systems, right? So I want to say here that there are there exist different notions of complexity that go beyond the complexity of perception action loops that we have in autonomous vehicles. I think that a lot of the discussions today about agentic AI and physical AI really zoom in into robotics, but I think that there's an entire world out there of large-scale systems for which we have no human operators. And so I do think that in this particular case, rolling horizon optimization, MPC, and distributed optimization is the viable option. And so one of the questions here is how do we handle the increasing complexity when we have large-scale systems? And for the case of robotics, these large-scale systems can be swarms, for example, right? That they have to operate in a very dynamic and changing environment. So what is next in optimization, right? And so here, my presentation basically will have two parts. The first part is going to be on our view on what's next on optimization. And then the second part will focus more on stochastic optimization and applications to off-road navigation. And then I'm going to conclude. And so again, there are many interesting applications out there where we have to go and deploy optimization. And what we want from the decision-making architectures, we want to be interpretable, we want to be scalable, right? We want them to work very fast, especially in the context of rolling horizon optimization. We want them to be real time. We want them to be able to satisfy constraints. We want them to be able to generalize, right? So we want to be able to tune an optimizer and being able to deploy it to the real world without having to tune it. Ideally, we would like to have some generalization guarantees. And then if we work with neural networks, we really want these neural networks to be small because there's always the case that we will have to retrain them. And I don't think that the economics will work here if you have a huge neural network, right? And so what my message here is that I think that the way to go about creating these decision-making architectures is this concept of deep unfolded neural network architectures, which essentially brings two worlds together. It brings the world of deep learning and iterative optimization together. And so the idea is that you can have an optimizer, you can unfold this optimizer, you can treat parameters of the optimizer as learnable parameters, and then through supervised learning, unsupervised learning, semi-supervised learning, or even reinforcement learning, you can actually train these unfolded neural network architectures to learn the solutions of the optimizers. And the idea here is that because the structure of the neural network architecture is given by the iterative optimizer, by the unfolding of the iterative optimizer, the constraints are all embedded in the architecture, right? So therefore, that architecture will satisfy the constraints. And so from an iterative optimization perspective, we should see the deep unfolding neural network architectures as an approach that really generalizes iterative optimization, because after you have trained that architecture, you can actually test it on different instantiations of classes of problems that belong to, instantiations of problems that belong to the same class. And at the same time, it overlaps with generic neural network architectures. But here I would argue that it's really difficult to get a black box neural network architecture and make it to have all of the characteristics of deep unfolded neural networks in terms of their ability to satisfy constraints, right? So when we optimize, we're optimizing and we are looking for the best solution within a feasible set. And so, from the perspective of how does this relate to the mainstream AI, I want to say that deep unfolded architectures basically incorporate domain knowledge, and at the same time require less data, right? So the more domain knowledge you put into the architecture, the less data the architecture will actually require. So we have these two extremes here. In one extreme, we have the black box deep neural networks. On the other extreme, we have optimization informed neural network architectures. Another keyword that you can find this concept is model-based deep learning. And this is work that goes back to 2010 from a paper by Carol Gregor and Jan LeCun. Since then, there has been a lot of work of deep unfolding for applications to signal processing, image processing, compressed sensing. But what my lab has been focusing more recently is to take these ideas and see how we can use the deep unfolded architecture for optimal control problems, large-scale optimal control problems, and distributed optimal control problems. And because we have developed all of these optimizers in the past, now we are in a good position to unfold them and basically learn these architectures. And so I would like to start from a paper that we recently published in ICLR, and this is the work of my student, Avustinos Saravanos, where the goal is to actually learn the solutions of large-scale quadratic programming problems. Quadratic programming is everywhere, especially in optimal control. We see it in sequential quadratic programming, linear quadratic regulators, differentiable dynamic programming. And so the idea here is that we have a optimizer, we have a quadratic cost, we have inequality constraints. And what we're going to do is we're going to get a very famous optimization method, the OSQP. We will develop its distributed version. So here we will essentially split the problem. We will introduce this xi variable, right? And then we have the consensus variable wi to essentially break the problem into smaller subproblems. And then we will follow the typical step of OSQP of relaxing the inequality constraints by introducing the variable z, and then having another consensus variable s to make sure that we are always solving the same distributed optimization problem. So now that we have the distributed version of OSQP, we can write the augmented Lagrangian, and based on that, we can derive a algorithm which has essentially three steps. It has the local update steps that optimize for X and Z. We have the local update steps that will optimize for the consensus variables S and W. And then we have the local updates for the Lagrange multipliers. And so now what we're going to do here is we are going to unfold this optimization method, like we are going to unfold the iterations of this optimizer up to a certain number of iterations. And we are going to treat certain parameters like nu and alpha and rho. These are parameters that are used within the augmented Lagrangian representation. We will treat them as learnable parameters. Another way to explain this is that by looking at the equations of the optimizer, we can think of these equations as a dynamical system. And we can think of the parameters as actually control parameters. And these control parameters can be represented in an open loop fashion. You can have essentially a parameter for every layer, right? Or they can be represented in a feedback form, where now we will bring small black box neural networks, like feed-forward neural networks, to actually represent these parameters as functions of the optimizer from variables of the previous iteration. So there is this open loop representation of the learnable parameters and feedback loop representation. And so now, when we are unfolding this architecture, right? Now I have a neural network architecture in which every layer of the neural network architecture is an iteration of the distributed OSQP method, right? With learnable parameters, which I can basically learn by having a training loss, right? And I can backpropagate gradients through this um, architecture based on these training laws. And so, uh, so how do we train this, right? So you typically start with limited data. Limited data means that you really need to set up your optimization here. You need a cost function, right? These are data that you typically get from an application. Um, uh, the cost function design actually is the part where in many problems in the real world one has to spend the most time, but then you pick an iterative optimizer, which you will unfold. The iterative optimization basically will give you the structure and the data you need to do the training, right? Because now I need to create training data. I need to use the iterative optimizer to generate multiple instances of quadratic programming problems, which I'm going to be used to perform the training in a supervised learning fashion. There is work. I mean, you can do the training in a semi-supervised learning way if you treat as a training loss actually the objective function of the initial optimal control problem. And people have actually tried to learn deep unfolded QP architectures with reinforcement learning. Of course, supervised learning is the most efficient way to train these architectures. Another thing that I would like to say is that once you start unfolding these architectures, one of the issues that may appear is that you may end up with an architecture that's really hard to fit in memory. So for some sub problems that you are solving, it's actually good to incorporate implicit differentiation. So that allows you to essentially compute gradients without having to unroll sub-optimization problems inside the unfolded architecture. So there's a interesting trade-off here in design choice in terms of using explicit and implicit differentiation. And so now when you take this and you have trained this architecture on a training set, and you test it on a test set, then you want to be able to see how well you can do. And this is just like some examples that show how fast. What we saw here is examples of different quadratic programming problems from random QPs with inequality constraints to random QPs with equality constraints, double integrator optimal control, oscillating masses optimal control, portfolio optimization, and problems in machine learning. And so what we see here is the same signal, the same result that we have seen in the signal processing and image processing communities, that the deep unfolded architecture has an unprecedented speed. It can outperform the iterative optimization, the iterative optimizer that we use to create the architecture. But at the same time, right, we have all the benefits of a neural network in the sense that we don't have to tune the optimizer. We have a neural network that has an architecture that is interpretable. And then the next test was to say now, can we go into large scales and work with much larger optimization problems that we could not, even the QP problem, we would not have been able to fit into memory. And again, here we see exactly the same thing. Like, for example, we see that on the left side, we see the optimality gap for all of these classes of problems. On the right side, we see the total wall clock time, and the outperformance of deep unfolded optimizer, distributed optimizer for these large scale problems is actually exceptional. Like, we can reduce the total wall clock time by 50%. And this can be further improved if you had another module that was able to learn the initialization of the optimization method. And so then another question that came up is whether or not we can certify these deep unfolded network architectures. And what we mean here with certification is to be able to bound their generalization capabilities, how well they will generalize. And so what we use here is a pack-based bound, and where you have a learned distribution and a prior distribution over the weights of the neural network, of the weights of the unfolded neural network. And basically, when we tested, we saw that we can say that the deep unfolded architecture can actually reach that bound within 20 iterations, while the iterative optimization counterpart would need many, many iterations to be able to reach the performance that we will get from the pack-based bound. So in these plots, the blue, I forgot to mention that, is always the iterative optimizer. And we have also incorporated all the adaptive schemes to make these optimizers to converge very fast. And so now that we work in this space, our next step was to go to nonlinear programming and see, okay, now that we have a QP optimizer, can we go and solve actually nonlinear programming problems, right? And then here, the goal is to essentially have sequential quadratic programming. SQP is used a lot in model predictive control, in trajectory optimization, right? The question is, could we take all of this deep unfolded methodology and see whether or not we can have a deep unfolded architecture for sequential quadratic programming problems. And what we realize is that for this particular case, for the case of nonlinear programming, we need an always feasible optimizer. We need a QP optimizer that even when the problem is infeasible, it will actually try to minimize that infeasibility. Because what happens many times in these nonlinear programming problems is that in the initial states of the optimization, you may have infeasibility, right? But what you really care is as you're reaching the optimal solution, that at that point you are feasible. So we want a QP optimizer that is forgiving, but at the same time, it can converge fast. And so this is just a plot that shows the benefit of the thing that we developed, which we call Deep Flex QP, and a comparison between the SQP, the non-unfolded optimizer, and the benefit that you have in terms of solve time, which was for us a very good result. And so again, we go back to quadratic programming. What we will do here is we will introduce this elastic representation. We will essentially get these constraints, and we represent them with the L1 norm that has benefits also in terms of speed. This L1 norm actually can very often lead to very fast convergence, because this L1 norm penalizes a lot in when the violation is very small, and it has this notion of sparsity. So it will basically try to penalize more the constraint that violates that is violated the most. And so then once we have this elastic programming representation, we will reformulate by introducing these variables z inequality and z equality constraints. And then we can now use the operating splitting approach to essentially split the problem into two problems by introducing the variable x tilde, and then introducing the constraint that basically says that the x tilde has to be equal to x. And so now we can again derive a scheme that optimizes for this quadratic programming problem with the L1 penalties. We will write the augmented Lagrangian as we did in the previous approach, and then we will treat parameters of the optimizer as learnable parameters, right? And so then we will unfold this architecture. We will introduce, we will have the open loop and feedback loop representation. And for the feedback loop, we will use small neural networks to represent the open learnable parameters. And so then when we go to apply this to, again, the same classes of problems, we could actually even significantly outperform our previous method, the deep OSQP, on all of these classes of problems, from random QPs with equality and inequality constraints, support vector machines, portfolio optimization, lasso, Huber fitting, double integrator optimal control, and oscillating masses. And all of these problems have actual constraints, right? So now we have an architecture that obeys the constraints, is able to outperform the iterative optimizer, and when we deploy it to problems that are on our test set, we don't have to retune the optimizer. And so we got some feedback from the reviewers that the problems that we were working were small scale, and we try to actually apply these methodologies to this methodology to large-scale QP problems to the extent possible, because after some point you have to incorporate another layer of distributed optimization to scale further. But even for much larger QP problems, we saw a significant benefit in terms of the total walk log time. So I want to kind of say here that you can see on the plots on the left-hand side that for the problems of portfolio optimization, the standard OSQP method will require 600 seconds, while the deep flex QP will require 15.3 seconds. So we have almost a 40x improvement in terms of conversion speed. And so this is the part of my talk that covers the optimization aspect, in the sense of bringing deep learning to speed up optimization, scale optimization, and take optimization out to the real world without having to go through the process of retuning. I think that this type of deep unfolded architectures will be really a significant part of the autonomy stacks of the future. And then I want to go to the next part of my talk, which is about now going to stochastic optimization and model predictive control. And so here I just want to give a little bit of a historical perspective on one of the algorithms that is used a lot right now is model predictive control and model predictive path integral control, MPPI. And I really want to, this is the work that we started with my student, Grady Williams, back in the summer of 2015. Actually, it was spring of 2015 where we team up with another group here at Georgia Tech, and we had this access to these really nice platforms, the GT Auto Rally. And so at that point, we had derived MPPI based on the idea that, okay, we can derive it for stochastic processes that have certain characteristics, and these stochastic processes essentially are affine in control and noise. But then the paper got accepted in ICRA in 2016, and then in 2017 and later in 2018, we actually improved further our algorithmic work by actually showing that, okay, you can have the same pretty much derivations for systems that do not necessarily have to be affine in control and noise. You lose some connections there with the classical theory of stochastic optimal control, but from an algorithmic perspective, you get a very flexible algorithm. And then in about 2019-20, we really moved to a bigger track here at Georgia Tech that allow us to see a lot of limitations of our previous work. Like that change, going from a small track to a big track, allow us to do more experiments for longer time, and then ask the questions of robustness. So at that point, we derived the robust MPPI, which was a version of MPPI that was more aggressive, and it was really taking into account low-level feedback gains that we were using to do tracking control, and kind of push the performance in terms of how fast we can go and how aggressive we can go. Of course, now there's a lot of work on MPPI. Many people are using it. There are many variations of MPPI, and I would say that I'm super excited to see all of this work that comes out from different labs, from different universities. This is really great and fascinating. And if I were to kind of cluster the different research areas around MPPI, is that many people try to work on introducing safety filters in MPPI. There's a lot of work around control barrier functions and MPPI. There's another area of work that tries to improve MPPI in terms of its ability to explore the state space and find better local minima. A lot of work around Stein variational inference, Stein MPPI, Gaussian mixture MPPI, and then more recent work on using MPPI as a planner for reinforcement learning, such as temporal different MPC and its variations. I think this is also very interesting work. And then I will put the rest as a fourth class. So we worked the last few years. We worked on much bigger vehicles, and we were also part of the DARPA Racer competition. And here I just want to show you one of the most recent videos that we managed to publish. Here I want to acknowledge the really great collaboration we had with JPL, and it was really great to be able to have this experience of getting all of these vehicles, going out to the real world, and deploy model predictive controllers. And here, what you can see is you can see MPPI basically replanning. There is uncertainty propagation. You can see the ellipsoids in the trajectory that MPPI creates. So it was definitely a humbling experience. I think we learned quite a lot, and that's what I'm saying. This is what I mean when I say that, yeah, it is important to say that MPC is the future of artificial intelligence, but I also think it's important to actually do it, because I think this is where you can see, when you take things in the real world, you can see issues, gaps, or where the next investment should be in terms of science. And so just a recap about MPPI. It's a very simple method. Basically, it starts from this interesting and in some ways weird inequality. Many students are asking me, why do we bother with free energy? How is it possible that this concept comes in stochastic optimization? And it all has to do with the fact that, if you take these P and Q probabilities and you map them to certain class of stochastic processes, this free energy becomes a value function, right? And a value function is well characterized in stochastic optimal control. I just want to say that really there was a lot of work in optimal control, like before MPPI. I think there was a lot of work here on risk-sensitive stochastic control. Control theories were really interested about robust control. So what happened here is that we basically flip a sign, right, on the free energy, and suddenly we have a change in the inequality. So, what we saw, it was what our interest was is to basically take this inequality and really try to see how we can benefit from that by in terms of algorithms, right? Because at the end of the day, you want to really have algorithms and that can work on real systems. And so uh, you based on this inequality, you can find an optimal distribution, right? And that optimal distribution, if you plug it back, that will give you the free energy. But then because it's really hard to, you need to use this optimal distribution at the end of the day to optimize for actual control policies. What you do is you parameterize your control policy as a trajectory of controls, and then you set up another optimization problem that essentially tries to match that optimal distribution, right? And so you end up with a very simple formula that you can implement on a GPU, and it is a weighted averaging. So it's really what we learn over the years is that people really like to go back to this derivation, even though there are multiple derivations and views of MPPI, because I think it is very simple at the end of the day, and it's very flexible, right? So in MPPI, you can have a cost function that is non-smooth, and that was really very flexible for us. And so I really want to talk about now four kind of proof of concepts in terms of things that are really interest to us in my lab, things that we think are important. So the first aspect is a paper that we published in ICRA last year, which is how do you incorporate visual features in model predictive control, right? And you always want to be able to anticipate things that will happen. You always want to anticipate the structure of the terrain, update your dynamics based on that, and make better decisions. And this is the architecture here. I'm not going to go into details, but what the basic modules of this pieces of this architecture is we use the Dino V2 to get features from images. This feature vector is a vector that is almost 400 dimensional. Then we do a PCA dimensionality reduction to go down to 40 features. Then there is also another neural network that further shrinks that space to a latent space of dimensionality 4. And then that feature vector of 4 is an input to LSTM that will essentially gives us a good prediction of forces, right? And so then that model, that augmented dynamics model, is going to be used in model predictive control inside MPPI to essentially make MPPI anticipate what are the forces that the vehicle will experience based on the visual information. And yeah, I mean, we took this architecture to the real actual vehicle, and we did testing, and we saw that yes, we can actually better predict the position of the vehicle. Here, I want to say that we don't have a direct access to force. We essentially estimate force through state. So the better we can predict the state of the vehicle, that is that's a signal of how well we can actually predict the underlying forces. So I think this is a very interesting research area. So far, we have been thinking about perception in the sense of creating cost maps, and which basically will give us a cost function, which then an MPC will optimize. But in this particular case, we try to move in the direction of using this visual information in the dynamics to improve the prediction process, and then make our MPC controller to anticipate more the terrain that is sees ahead of it. Another place where I think it's a place where we are currently active is there's a lot of work about safety, right? Many people aim to make MPPI to be safe by using control barrier functions and essentially creating a two-layer architecture where MPPI plants creates the trajectories, and then you have a filter, a CBA filter that will try to stay as close as possible to the reference trajectory provided by the MPPI, but at the same time trying to satisfy the safety constraints. And so what typically happens in a lot of papers that we have seen is that because this optimization problem is hard to solve in real time, you end up getting the CBF constraint violation as a cost in the MPPI formulation. And so what we thought here is what we ask here is the question, can we use all of these techniques that we develop for deep unfolding to actually learn very fast the solutions of CBFs and then incorporate the unfolded Flex QP architecture inside the pipeline? And the answer is yes. That's a very recent work. We just archived it last week. But basically, what the plots here show is that we can speed up the optimizer. We can make MPPI to be more successful, reduce the number of collisions, and again, have a very fast safety filter. So I think that there's a lot of interesting work in this space. Here, what I'm showing just a proof of concept. Another place where it's really interesting to us is whether or not we can go beyond sampling-based optimization, and whether or not we can deal with non-convexity that we typically have in robotics and create a scheme that blends the gradient-based optimization with sampling-based optimization. And the motivation here comes from the idea that, okay, one way to create this new hybrid approaches is to basically have iterative optimization run, let's say gradient or Newton optimization run for a few steps, stop, sample around the current state of the optimizer, see if you have a better solution. If yes, you pick that state and then you continue with the iterative optimizer. And so there's this disruption process, right, where you let the gradient descent or Newton optimizer to follow a few steps. You disrupt the process by sampling. If sampling gives you a better solution, you pick that better solution. If not, you just continue the gradient descent process. And so the way how you can do that is by incorporating these entropy regularization terms in the standard trajectory optimization methods. And you can do that with different types of entropy. You can do that with Shannon entropy, or you can use non-extensive entropies. With Shannon entropy, you can preserve the compositionality of optimal control, which means that you can essentially create a mixture of optimizers. In the case of Chalice entropy, that this compositionality property is not preserved, but the way how you can handle the lack of exploration is by the fact that in the Chalice entropy you get a distribution that has flat tails, and therefore you can sample from spaces that you wouldn't able to sample by just using a Gaussian distribution. And then other disruptive mechanisms that we have been exploring is this idea of Newton-Stein variational, which we incorporated inside trajectory optimization methods such as differentiable dynamic programming. And then here just a example that shows that compares the different methodologies from MPPI, style variational MPPI, mixture of Gaussians MPPI, and then we have unimodal maximum entropy DDP, multimodal maximum entropy DDP, and Stein variational DDP. And then you see basically that this entropy regularized hybrid schemes can actually outperform MPPI. Now, I have to say here that we actually still learning from this experience because we really wanted to take these methodologies, the multimodal and unimodal maximum entropy DDP to GPUs so that we can have a fair comparison in terms of computational speed with MPPI. And we are in the process of overcoming some issues that have to do with differentiation and how you can implement differentiation on GPUs. And so the last thing I want to talk about is uncertainty propagation, and that's something that we saw in our work with bigger vehicles on model predictive control. In that, in essence, model predictive control is great, but there is always this issue that the feedback mechanism is explicit, right? So all the steps after the first step in model predictive control are open loop. And so now imagine the case where you have a vehicle and you want to go through a very narrow corridor. Model predictive control can be conservative because it thinks that just only after the first step, everything else is open loop. And so the idea of propagating open loop and closed loop uncertainty and what is the impact of that in the performance of a closed loop system when this closed loop system is controlled by an MPC controller, I think that's really a question to us in terms of how we can develop model predictive controllers that actually incorporate explicit feedback in the prediction process so that we have more intelligent and aggressive and optimal, in some sense, behaviors. And this is not the same thing with tube-based NPC, right? In tube-based NPC, you just try to react to disturbances. Of course, one may say you can characterize the tube, and we did some work on this space too many years ago. And if you have a characterization of the tube, you can also use that in the prediction process of MPC, but then you have to do a lot of offline work on learning that tube and so forth and so on. And so back to key messages, and I don't know how I'm doing in terms of time. I think surprisingly, I'm doing good. I want to say that there are two paths towards agentic and physical AI, and I'm really I think nowadays I have to use this terminology, okay, about agentic and physical AI. One path is the path that relies on imitation learning, right? You have some expert, you get data. This path requires a lot of data, and from my point of view, it lacks interpretability, right? And I think interpretability is a big issue, right? Like as societies, as scientists, when we want to really advance our societies, when we want to deploy systems that are more intelligent, we really should care about how well we understand them, right? And then there's the path two, which relies more on optimization, right? You don't have somebody to teach you how to solve the task. You really have to actually sit down, design an optimizer, tune it so that you can solve the task. That might not be always easy, or it may not be the most favorable thing to do, but it is interpretable, right? It will require less data for the most part, and as I said before, it will be more explainable. And so the key assumption here, like to make this comparison, is also that data is for free, which is not the case. There are many applications in which you have no demonstrations. And I'm sorry. And then I want to say that there are different forms of complexity in the real world. Like very often we talk about physical AI, autonomous vehicles, robotics, but that's not the only complexity that exists out there. There's also the complexity of scale in large scale networks. From a robotics perspective, a network could be a swarm, and this type of complexity is not part of the discussions about the role of artificial intelligence in the next like 10 15 years. And so we just always focus on things for which we have an expert, right? And then we can have all of this discussion about making the comparison with a human, which I find not to be really very interesting. I think the biggest problems are in problems that are characterized by the complexity of scale and how we handle that, right? And then my last message is that, deep unfolding really, from my perspective, checks all the boxes in terms of transparency, constraint satisfaction, scalability, generalizability. Of course, this type of work goes against the idea of one architecture fits all, that there's going to be one big neural network that is going to solve all decision-making problems. I really do not believe that, and I have not seen that happening in any shape of form in any of the problems that I have worked on. And so this is the last slide. I know that we have students in the call, and I want to really just say that there's a paper that has really uh, uh, um, affect me in some ways in terms of how to think about the role of control, artificial intelligence, optimization. I just want to talk about or remind people about this very nice paper written by Ganderstein on respect the unstable. And I would like to just read these two quotes from his presentation, just to talk about the ethos of that era and where we are today. So in the first quote, when he gives his presentation, I think it was in 1989, that was the first body lecture. He says, the controls group is a very successful group. Think about control systems. They are in our houses, they are in our cars and transportation systems, they are in our factories and military systems, they are everywhere. They work, and we hardly ever notice. So we are enormously successful, and we should be proud of that. But what issues do we have? And then he continues by saying, we certainly place a lot of mathematics, a lot of value in mathematics. I think we are doing it at the expense of real physical consequences of some of some of the things that the mathematics describe. If someone accepts that, then these two trends are in opposition. We at the moment are a very respected society. Society around us let us control things that are dangerous, more and more of them. They trust us. Our technology is well respected, and no one questions question it, basically. But if the two trends continue, that might not be true. We may, in fact, join the other areas of technology in terms of how trustworthy we are. I think these messages are really very solid. And so a community at that time that was a healthy community in terms of trying to identify what are the real issues and what's the position we should have with respect to what society is asking from us to do. And so I really try to put some of these thoughts in an opinion paper that I wrote, and I would like to invite people to give me some feedback. With that, I would like to thank again for the invitation. It was definitely great. I appreciate the fact that you gave me the opportunity to express my views. And I really want to acknowledge here my students. I want to talk about Saravanos, Agustinos, and Alex Osin, who led the deep unfolding and distributed optimization work. The work on off-road autonomy is by Jason Gibson and Bogdan, who will soon graduate. And of course, I want to acknowledge students who graduated with me, Grady Williams and David Fan, who are right now working on companies that work on the space of off-road autonomy. Thank you very much. And these are my sponsors, support, and I'm open to take any questions you guys have.
Thank you, Professor, to share the interesting talk and also your thought on our control like society, the unstable perspective. So we do have some questions from the audience. First, from Professor Andreas Malikopoulos. He brought the thanks and to you, and also he had one comment, a question about he was wondering if you can comment on how communication delays between agents can be handled in the MPCA plus RL framework.
There is, I can speak about one of our recent papers that we actually wrote on asynchronous ADMM for multi-robotic systems. I can send that paper, but basically it's all about how you are updating your agents and in the ADMM formulation, there's a raw parameter that you have to update, and that raw parameter is a function of the delay of its agent. So my answer is there are ways to handle delays, and that will you could handle that by the way of how you tune the raw parameter, which is basically the parameter that is important for achieving consensus and mapping that parameter to the delay of its agent to make a decision. That's a paper that we just archived about a week ago. I did not have time to have it on my presentation, but I'm happy to share it with broader audience.
And there's another question. Out of curiosity, what's a typical horizon for prediction when visual information is incorporated into dynamics prediction?
I will have to. I don't remember the number. It's interesting that I was just discussing with my students about this, but I don't recall the number. I will. It is in one of these paper. It is in one in our paper. I don't remember the precise number on top of my head right now.
Okay. There is another question. the audience is wondering regarding of using deep learning to solve the optimization problem. How shall we balance the complexity of neural network and the generalization of the solution?
How do we balance? Um,
The
uh, I don't have an answer in terms of having a theory, right? That says because the complexity. Let us think first. What is the complexity here? These are unfolded architectures, right? So I'm unfolding the iterations of each of an optimizer. So the more iterations I have, the more open parameters I have, the more small neural networks I will have. And uh, so we don't have an answer yet to that. But one thing that I can say is that these architectures are actually work very well for the particular classes of problems that you have. So we are not talking about, here of hundreds of thousands of parameters. These are very, very small models. And one of the reasons why they have been used in signal processing and image processing is because they're also very energy efficient. You have very, very few parameters. Uh, uh, yeah.
uh, Regardless of the time, I just have one last question from myself. It's an extension of this generalization problem. So the imitation learning typically they suffer from the like covariance distribution. If in the real world the distribution may shift, then you have the compounding error loss. I just wondering like in the professor when you propose your framework, you also like using neural network and it's also the supervised training method you are using. So do you also suffering from this like compounding error amplification during the real world deployment, and how do you avoid this like or minimize?
Yeah. So in the real world, I think we have to really answer this question, we would like to basically take one of these unfolded architectures and put it in one of our vehicles and do imitation learning. It's just that right now you do imitation learning based on the unfolded architecture, right? So I would expect that, and I'm just hedging right now, right? That the unfolded architecture will actually generalize better because like it's really uh, you basically deploy an optimizer that you don't have to tune. Okay, you basically deploy an optimizer that you do not have to tune. So optimization should be able to give you the tail of the distribution that you want, right? But that's something that it's something that we should test, we should demonstrate it.
Thank you, Professor. It's a great honor for you as our close mark speaker for this semester. And I really enjoyed today's talk. And also for the audience, um, please also keep in mind we also have a next semester. We also keep doing our seminar. We will have more interesting talks in the following semester. And thank you.
Thank you.
Bye bye.